My name is Nico Schiller, and I want to talk today about drone security and the mysterious case of DJI's DroneID. So, first of all, I want to talk about consumer drones. Consumer drones are a mainstream product, so you can buy them everywhere, and you can fly around and have fun with them, take cool pictures and videos. And they have a really high popularity today. But you can also use your drone to fly near an airport, for example, which mostly disturbs the air traffic and which leads to expensive shutdowns. Furthermore, you can also fly near prisons and bypass physical barriers to trap weapons or drugs into the prisons, for example. So this high popularity of consumer drones set a low entry barrier for air mobility in a traditionally heavily related sector. But the vendor knows these problems, so they apply different countermeasures on their drones. For example, they apply position tracking on their drones. In our case, here DJI sells a device which is called Aeroscope, which can track your drone. Furthermore, the vendors apply software limits to their drones, for example, geofencing, so you can't bypass restricted area or fly into them. And finally, there are also hardware protections to secure the device itself. So, for example, the vendors disable the debug interfaces on the devices and something like that. But the question is now, are these countermeasures sufficiently implemented? Well, I will show you in this talk how to dissect such complex cyber-physical systems. And we will start with the wireless physical layer. So I want to show you how you can analyze the wireless physical layer and how you and your drones are tracked. Furthermore, I want to show you how you can statically analyze the firmware and the hardware of such a drone, and if the firmware signature can be bypassed, for example. And finally, I want to show you how you can dynamically analyze your drone or the drones to find vulnerabilities in an automated manner. So at the beginning of this project, we ask ourselves which vendor or which drones should we analyze. And we set our focus to DJI drones because DJI are the biggest vendor in the drone consumer market, and, which is more important, they take security serious. So they have a security white paper where they describe their countermeasures which apply to their drones, and they have also a bug bounty program where you can submit your bugs and get some money for. And finally, they also made in the past some inconsistent statements about their transmitted signals. So they misspoke on some points, and that's what we were looking also for. So as I said earlier, DJI sells their Aeroscope. So Aeroscope is a receiver which are sell to law enforcement. So for example, to prisons and also to airports to track down the drones. And DJI made some statements in the past about the transmitted signal, which is called DroneID, which can be received by Aeroscope. This signal said DJI is encrypted and can just receive by the Aeroscope device and not by other users, for example. So that was interesting for us, and so we had a look into this. For this analysis, we use cheap common off-the-shelf hardware, in our case SDRs, to analyze the wireless physical layer. And for this, we first scanned the wireless physical layer, and we found a broad signal, which you can see here in the middle. This broad signal, we assumed, is the so-called DroneID packet. So we built some kind of packet detection to filter out these packets from the wireless physical layer and the signal. And we can now analyze the signal. So we analyzed it with different frequency techniques and radio techniques. And we get a lot of information from it, like the duration of the signal and also the bandwidth and other stuff we can use later to synchronize our receiver with the transmitter. So the receiver is our SDR and the transmitter is the drone. If we applied the synchronization steps correctly, we get a byte stream which can now be demodulated. In our case, the modulation of the signal was done by QPSK. So we built some demodulation steps with QPSK to get a demodulated bit stream. This bit stream is then fed in our decoding stage where some magic happens. So for example, the descrambler and also the turbo decoder. And that results in our final data. So our final data shows us that the signal indeed is not encrypted and can be received by everyone which owns a cheap SDR, for example. The data furthermore show us that these DroneID packages transmitted the position of the drone and also the live position of the pilot. So if you walk around with your remote, they can track you. So the next question we ask ourselves is, can we spoof or maybe disable this transmission completely? So we provide a fake location to the remote control and to the smartphone, and it works. So our pilot were somewhere else as a drone. Furthermore, we found in the later analysis of these drones that we can also completely disable the DroneID transmission, which shows us that this countermeasure is not applied sufficiently. So now let's talk about the drone's hardware. And let's perform some basic analysis steps to go deeper into such a system. So you can tear down your drone or the remote control to have a look at the PCBs and to analyze them. For this, we use a DJI Mini 2 and its remote control. And we analyze both with logic analyzers and also oscilloscopes. And on one of the PCBs, we found some kind of boot screen. This boot screen shows us, seems to be a bootloader which loads different parts of the firmware and then shows us a log message which indicates that all debug interfaces are disabled and also that the drone switches to some kind of production state. Oh, sorry. So to get a better knowledge of the boot process, we checked the firmware of the bootloader, and we found that it seems that we can send 3 magic values to the bootloader via USB in our case to get some kind of interactive bootloader mode. So we tried it and it worked. We unlock the bootloader and get this interactive mode where we can flash our own firmware. So the next step for an attacker would be to modify the current firmware and to upload a custom firmware. But DJI applied their countermeasures to the firmware as well. So they signed their firmware, and if we modify the firmware, the signature gets invalid. But there were also some other files which are not signed. We identified these files as patch files. So in these files, there are some memory addresses specified and also bytecode, and the bootloader loads these files after the whole firmware is loaded and applies the patch to the firmware. So our idea was to finally forge our own patch files and to prevent the drone from switching to the production mode. So we did this and it worked. So we get finally a UART console on the transceiver of the drone, which allows us to dump memory and also to read log messages and to write into the memory. Well, that was a lot of manual static analysis, but it shows us that it's not that hard to get into the system of a drone, even if the firmware is protected. Now, let's check out how we can dynamically analyze such a system and how to find vulnerabilities in an automated manner. For this, we used fuzzing. Fuzzing is a state-of-the-art technique which is used to fuzz for example, programs or fuzzing targets by sending random inputs to the targets and observing if these targets are crashing. If this happens, a crashing input is found and you found maybe a vulnerability. So the question here is how to fuzz a real drone. So our idea was to fuzz the complete hardware. So for this, we need a fuzzer and also a drone. And we need to specify an interface which can be fuzzed later. So on DJI drones, they have a USB interface where you can connect your computer with to make updates or something like that. Over this USB interface, DJI spoke a protocol, a custom protocol which is called DAML. This DAML protocol is also used inside the drone to speak with all or to communicate with all interfaces. So we built a protocol fuzzer for the DAML protocol and applied our fuzzer to the drone. The next step you need is some bug oracle. So if a crashing input is sent to the drone and the drone is crashed, you need some way to observe if there is some bug. For this, we also used the USB interface as a simple bug oracle, because if the firmware is crashing and the drone is rebooting, the USB interface gets disconnected. So that's really simple. But what is if the fuzzer triggers some undefined behavior in the drone, which can be observed by a crash of the firmware, so by a reboot or a disconnection from the USB interface? Well, we had a look at the accessories which you can connect to the drone, which is in our case the remote control and also the smartphone. So on the smartphone, you can display a live video feed from the camera and also some telemetry data from the drone. So our idea was now to build some UI oracle, which periodically checks the DJI app on the smartphone, go through the app, compares different values which are predefined, and checks if there some modification exists or some failures occurred. Since we fuzzed the complete hardware and the drone as a complete system, we found during all bugs which we found during our fuzzing campaign are reproducible. So you can plug in your drone after the fuzzing campaign, replay the input, and the drone crashes or the undefined behavior occurs again. So the question is, does our fuzzing work? Well, yes, our fuzzer produces 15 bugs overall on different DJI drones, which are ranged from arbitrary code executions in 2 cases, and also one bug which we called identity spoofing, because the fuzzer triggers change of the serial number of the drone, which should be immutable. So the serial number is also transmitted in the DroneID packets, which I mentioned earlier. And if you change the serial number, you spoof your identity. The last 2 bugs were also notably found by our UI oracle. So let me give you a short summary of findings. Well, first of all, the position tracking seems not sufficiently implemented, since we were able to bypass the location steps, the location of the pilot, and we were also able to disable the transmission completely. Furthermore, also the protection of the hardware itself seems not sufficiently implemented, since we were able to re-enable the debug interfaces and we were able to bypass the firmware signature. So an attacker can easily provide custom firmware or modified firmware to the drone. And finally, our fuzzer triggers a lot of bugs, ranging from simple crashes to arbitrary code execution, which would allow an attacker to gain root access on their drones, which allows them to disable the software limits. So now I'm at the end of my talk, and let me give you some takeaways. First of all, it seems that the countermeasures are not sufficient, and it's hard to secure real-world devices since they are so complex. So you have different components in such a drone from different architectures, and it's hard to secure all these components because they are communicating with each other. So it requires holistic approaches to analyze such a complex system. So we need to analyze the firmware, also the hardware, and the wireless physical layer. You can check out our Git repo, and which will be available after the conference, I think. And you can ping me on Twitter if you have questions, or you can ask your questions.
For those bugs that you found, how did you actually go about figuring out sort of what type of bug they were? Was that just like a manual analysis of every crash, or you went and looked at the firmware, tried to figure out where they were crashing, etc.?
Can you read this a bit?
Yeah. For the bugs that you found, how did you actually go about triaging those bugs and figuring out sort of which ones were code execution, which ones were denial of service, etc.?
So we applied on one of these bugs a case study, or on multiple of these bugs a case study in our paper. So we checked out which component was. So one of these bugs we named the drone's name, which is not a problem at all because the user can also change the drone's name in the app. But the fuzzer triggers these renaming. So we had a look in the firmware, and we found that there was this arbitrary code execution. So you can insert your code into the Wi-Fi's name, and your code gets executed. So that was one point. And the other point was that for identity spoofing, the fuzzer source triggers this change of the serial number. So it was clearly that there was something wrong because the serial number should be mutable. And for all other bugs, we had also a so-called ADP check, which periodically checks if there is some other ADP device provided to the fuzzer, because DJI uses debug interfaces in their drones, which are mostly over ADP, so you can connect to this ADP port, but it should be disabled by default because it's production mode. And we also responsibly disclose all these bugs to DJI, and they give us a list with the severity and also provided us all bug details.
Hey, Yongde Kim from Quest. So, did you find vulnerabilities in the communication module?
No, not at all. So we didn't have analyzed the communication module, just the transceiver of the drone. So that was the firmware verification bypass, which I explained earlier. The transceiver is
Doing the fuzzing.
The fuzzing. No, I don't know. So I think most of the bugs were occurred in the flight controller, but I can't tell you the details where these bugs.
So those bugs could not be exploitable, right, in the flight controller. You cannot send any packets to the flight controller directly.
Yeah, you can send packets directly to the flight controller, and then I think there were some buffer overflows which occurred, but we didn't try to exploit this buffer.
But that's only after you successfully pair, right? So you need to pair your.
Okay.
So pairing should be solved to actually crash.
Yeah. So our first setup was to try to we connected the drone directly to the fuzzer with the USB port. So we fuzzed the drone directly and the components of it. And we had also another setup where we've connected the remote control to the fuzzer, and the remote control was connected to the drone via Opus, which is the proprietary protocol. And it seems that all commands can be relayed by the remote control to the drone. So all commands which we send from the fuzzer to the remote control gets relayed, and for example, the drone crashes as well. But you need the controller and the drone should be paired.
So attacker does not have the controller that is already paired with the drone, so therefore that part should be solved.
We assume that it's possible to inject such packets, but DJI uses frequency hopping on their wireless package, on their wireless physical layer. So the command and control link is hopping over the channels. So if you found this hopping sequence and you provide home packets with this dummy code, you are able to inject our vulnerabilities.
Do we have more questions? Okay, I need to explore this privilege again. So you conduct a comprehensive analysis of drone, right? I saw the physical analysis, static analysis, and fuzzing. Do you see any interesting or unique feature of drone security going to this analysis?
Can you repeat the last?
Do you have any interesting or unique features, challenges, findings in this drone security analysis? Because we have seen these techniques has been used for like IoT analysis, IT fuzzing, right? For drone security, what do you think is the most interesting part?
Yeah, well, I think the holistic approach is the most reliable or the most interesting part here, so that you have to look at all these parts together to get a real overview of such devices. And that you, and also our fuzzer, which uses this novel technique to observe the UI interface and check if there are bugs occur. And yeah, I think that's.
Okay, so for the fuzzing part, are you able to get any feedback from the Zoom device? Are you able to get any feedback, like the code coverage or any measurable improvement of the testing?
No, our feedback mechanism was we used this generational fuzzer, so or grammar-based fuzzer.
Okay.
Because our fuzzer is based on the double protocol. So we have a finite space of commands you can send to it, and we test all of them.
Okay.
So no real feedback mechanisms.
I see. So you can only see if it crashes or hangs or not, right?
Yeah, that's for a macro level.
Okay, got it. Thank you. Do we have more questions? We do have time. Oh, we got one.
Can you describe your experience in working with DJI to fix these bugs? Were they cooperative and receptive to it? Things like that?
Yeah, the experience was quite good. So we submitted all our bugs for their bug bounty website, and they answered quite fast and tell us that they are happy that we shared the bugs with them, and also for the further responsible disclosure process, they were really nice. So they sent us also feedback about different things we should send to them, and we asked them some questions about the bugs, and they were happy to answer all these questions to us. So it was quite nice to work with them.
Okay, last call. Any question?